welcome to my channel. Today I'll be taking a lecture on electric field. I want you to subscribe if you've not and follow along with me. I'll be dealing with a very important question where I would review some concepts you ought to know about the electric field, and particularly we'll be limiting ourselves to the question I'll be solving today. I hope you are able to follow along. This is the question we'll be looking at today. A rod 14.0 centimeter long is uniformly charged and has a total charge of minus 22.0, and this is a microcoulomb. Then determine the magnitude and the direction of the electric field along the axis of the rod at a point 36.0 centimeter from its center. Taking the important parameters first out, we would be looking at the length of the rod is given as 14.0 centimeter. We can write that as 0.14 meter. Now, the next thing we see there is the charge is given as minus 22.0 microcoulomb. Can write that clearly as minus 22 times 10 raised to minus 6 coulomb. So that is settled. We have to determine the magnitude and direction of the electric field along the axis of the rod at a point 36. So now, since it's at a point 36 from the center, let's imagine that this is the rod. From the center to that point is 36 centimeter, is equal to 0.36 meter. So if we follow along what we have here, we will discover that this is the point we're dealing with. So if we call this point point X, so in the case of if we call this point, this other one from the center of the rod, let's call this one A. Let's call this one A. Then, since this is from the center of the rod, we can tag this place minus L over 2 and this side L over 2. This will be relevant in the formula we'll be using because it's along the axis of the rod, definitely. Now, to be relevant in this formula, we are going to use this formula to calculate the electric field along the axis, that's the x-axis. We'll calculate it as normally we know the electric field, you have K, that is 9 times 10 raised to power 9, 1 over 4 pi E naught. So K, then we have modulus of the charge, Q. Let me just write it as capital Q now, over R square. Then we are going to dot it with 1 over L. Literally, we are just supposed to find the charge density, but now we are writing the normal formula for electric field, which you know. But in this case now, since we're dealing with the length of a rod, we find it per unit length. So 1 over L will be added to our formula. Then, considering the point we are talking about, would be integrating the whole of this, the whole of what we're written here now, from a minus L over 2 to A plus L over 2. If you look at it, this is the point A, from A minus L over 2 to what? A plus L over 2. Assuming it wasn't from the center, it was just from here to be from A minus L to what? A plus L. That will be the limit of what we are considering. So this integral will be with respect to the x. But now, since we have x, we have r, not x, we can write it as the r. So I hope you get that. Normally, we could have just written this as x, then we'll be integrating with respect to the x. But now, since we have r, we'll be integrating with respect to the r. So bringing out the constant, K a constant, the charge in consideration, modulus of the charge in consideration. The reason for the modulus of the charge being utilized is because, please take note of the important point I'm making mention of here. Electric field is never calculated to be negative. Why is electric field not calculated to be negative? Because it is the force per unit positive test charge. The electric field will never be negative because it is calculated with respect to a positive test charge. So that's why we're using the modulus of the charge here. So you get to understand some other concept as I flow by and by. A minus L over 2, A plus L over 2. We are integrating 1 over R squared now, the R respect to R. So if we go along, EX, we add K modulus of Q over L, integrating from A minus L over 2 to A plus L over 2, R raised to power minus 2. That 1 over R squared could be written as R raised to power minus 2 dr. Now EX will now be equal to, hope you can flow along with me. So it will be equal to K Q over L. This will now be R raised to power minus 2 plus 1 over minus 2 plus 1. The limit A minus L over 2, A plus L over 2. So we've integrated. We will now apply the limit now. EX will be K modulus of Q over L. Then we can let's resolve this before we apply the limit. This will be dot minus R raised to power minus 1. That's put the limit there. Now we continue. We have K over L. Can write this as dot minus 1 over R. The limit A minus L over 2, A plus L over 2. So now if we apply the relevant limits, we have a situation whereby this becomes dot minus upper bracket 1 over A plus L over 2 minus 1 over A minus L over 2. It now becomes, can move here, EX now be K, the modulus of this. If you take the minus that was initially here inside, it will become, there will be, the minus goes inside, then there is a switch. It becomes 1 over A minus L over 2, then minus 1 over A plus L over 2. So now you have this. We can now recall, we know our K to be 9 times 10 raised to power 9. Yes, as a constant. Then we know Q, the charge, is given as minus 22, but this time the modulus of the charge will now be 22 times 10 raised to power minus 6. There's a coulomb now. Then the length is given as 0.14. We've made mention of this before. A in this case 0.36 meter. So now we can implement them in our formulas. 9 times 10 raised to power 9. Then the modulus, that is times 22 times 10 raised to power minus 6 all over the length 0.14 into 1 over 0.36 minus 0.07. Definitely that is 0.14 divided by 2. 1 over 0.36 plus 0.07. So after doing the necessary calculations, you will arrive at this answer. So like I said before, this answer is positive. An electric field is meant to be positive. So since we calculated this positive electric field with respect to a negative charge, it means the direction will be towards the charge. Because a positive electric field is attracted towards a negative charge. because the positive electric field is a product of a positive test charge, of which I told you that electric field can never be negative because it's a function of what, a positive test charge. So if you have a positive charge in consideration, it will flow away from that charge. But in this case, the charge in consideration, not the test charge. The test charge of an electric field is always positive, but now the charge in consideration was negative. That means this electric field will flow towards the charge. Meanwhile, assuming we considered a positive charge, it would flow, the electric field will flow away from that positive charge. So electric field is always positive, flows towards negative charges, and flows away from positive charges. I believe you are able to get the point. So these tutorials, Petrolic, by a corner of my channel, you see a symbol there with a P and all that. That is the company that runs both my music and then my tutorials. That is my company. I hope you are able to subscribe and stay tuned for more lectures on physics. Thank you.